Hi, my name is Joshil Vaddi, and this is my Physics 2211 Constant Velocity Lab. Firstly, some of the principles of this lab includes Newton's first law. This law states that objects that are in motion stay in motion unless other external forces act upon the object. In our case, friction and air resistance can stop it. Newton's second law states that force is equal to mass times acceleration. Finally, constant velocity is a principle where the net force and acceleration are zero, due to there being a constant speed. Next, let's introduce the experiment. The purpose of this lab is to observe an object that is undergoing this kind of constant motion and has no net force, as well as to see the difference between the predicted versus experimental motion of the object. The formulas I use include the position and velocity update formula, which are right here. RF is equal to RI, so final position is equal to initial position plus average velocity times delta t, and then final velocity is equal to initial velocity plus the net force divided by the mass times delta t. And there's also used the average velocity formula as well. The experimental method includes a system composed of the slider object that is moving on the track. We will be moving this object and investigating its motion through a tracker. The surroundings include external forces such as friction and push force as well. The initial conditions include pushing the object and time being zero. The computational methods, on the other hand, is a predicted model using the GlowScript software, where the two update formulas are used to create a model that accurately tracks what would happen to the slider. Next, the diagram of motion of the actual object. So in this case, we only have two forces, force of gravity and normal force, both of which are equal and canceling each other out, meaning that there is no net force on the object. And only initially when you actually move the object is there an acceleration. But after that, there is constant velocity and the net force cancel each other's the forces cancel each other out to yield no net force. In constant velocity, there's no acceleration, so force is equal to zero. And this is shown by the Newton's second law, where F equals ma. And if there's no constant velocity, a constant velocity, there's no acceleration. So F equals m times zero. So F is equal to zero. In the tracker analysis, I tracked the position against the time, and it yielded a positive sloping p versus time graph with constant velocity. The object is moving from left to right as well. My computational analysis in GlowScript includes the initial conditions of mass equals 1, because that does not matter for the velocity in this experiment, as well as the initial velocity being 0.597, which I calculated using the average velocity formula. As you can see here, I did delta R over delta T, so position over time, the change in position over change in time, in order to calculate this initial velocity. I also did delta T of 0.03 because these are the time intervals, and I did this because I calculated the amount of frames and the step size, and using this I found 0.03 to be the best and most accurate. Next, let's look at the predicted method for the computational or predicted method of this. So in this case, I started by using the position and velocity update formula to update the velocity and position of the ball accordingly, and I also made the time to be less than 3.2 seconds. The F net, or the net force vector, is 0, 0, 0 because there is no net force on this object because it's undergoing constant velocity, so no acceleration. So via Newton's second law, F equals ma, the net force must be equal to 0. Next, let's look at the predicted versus observed graph. These two lines are very similar in this position time graph, where the x-axis has time in seconds and the y-axis has position in meters. As you can see, the blue is the observed and the red is the predicted. And in this case, we can see that the observed has a lesser slope than the predicted graph. They both show constant velocity. However, the observed velocity is less of a constant velocity and is less than the velocity of the predicted line, showing that forces such as friction may have made the velocity decrease. If you change the axes, then the slope of the line would be negative and go in the other direction. So instead of a straight line this way, it would be a straight line the other way. And it would also be a negative slope. But in this case, slope, the negative sign would just indicate the direction. And these small discrepancies you can see in the observed, for example, it's not a completely linear and straight line like the predicted one is. The predicted one is completely straight, but the observed one isn't. And that shows small discrepancies that show that it's not completely constant in terms of velocity. There are some errors in it that can be caused by force of friction, air resistance, the push force not having a constant, having some acceleration to it. So if I change the axes, we already mentioned what would happen if that occurred. And so is it possible to see how many forces are added together to give zero net force? In this case, you cannot really say this because there's always some acceleration when you push an object, and forces like friction and air resistance make it difficult to push an object in this case to give it zero net force like this. Thank you.